So, yes, okay, so we have started recording. So just a quick overview of the housekeeping rules. Please mute your microphone during the presentation so that we can hear our presenters clearly. If you wish, you may also close your camera. To facilitate the discussion, you have chat disposable at any times, and we can actually use these messages sent out during the presentations for a Q&A session afterwards. So the questions and the discussions can be posed also live after the presentation session. And of course, you are encouraged to participate actively. And just a quick overview of the agenda. So we have a quick welcome note, followed by an introduction to the STELAR and CrackSense project by our project coordinators. And these presentations will be followed by remote sensing for precision farming, and as well CrackSense presentation, proximal sensing for fruit monitoring. And these presentations will be followed by Q&A session afterwards. Feel free to participate. We have attendees joining as we speak. And we wish you all success, and let me know if you experience any issues in sharing your screen. Dimitris, I believe that your presentation is the first.
Okay, thank you very much. Just a second to share the slides. Okay, I guess you should see the presentation now. First of all, thank you very much, Marina, and also the team at Food Skill Hub for organizing this. And of course, many thanks to the representatives from the CrackSense project. It is very nice to meet you. And I hope this will be a very interesting webinar. So, starting with the STELAR project, first of all, to introduce myself, my name is Dimitris Koutas. I'm a researcher at the Athena Research Center in Athens and the coordinator of the project. I will provide a brief overview about the project itself and what we're trying to achieve. And then we will have later a more detailed presentation about the activities related to Pilot B. So as you can see here, the project is about spatiotemporal linked data tools for the agri-food data space. And it is an EU project funded under a call for technologies for data management. So data management is at the core of what we are trying to achieve in this project. The duration is 36 months, and actually we are almost close to the end of the project. And you can also find here the link to the website where you can find more information, results, link to the GitHub repository, and so on. Also, you can see here the consortium. We have 9 partners from different countries. I will not go in detail about each partner, but as you can see here, broadly speaking, there are partners coming from the ICT domain and leading the development of the platform and the toolkit, as well as partners from the agri-food domain being responsible about the piloting activities. So, what are, let's say, the main challenges, the main problems that STELAR is trying to make a contribution towards? Our focus is on data pipelines and data preparation for AI applications. And this is, we believe, a very important topic because usually the focus tends to be more on the machine learning and AI part, like model architectures and training and so on. However, the data preparation aspect, which sometimes receives less attention, is very crucial and to a very large extent determines the success and the performance of these downstream applications. So this is a part where data scientists tend to spend a lot of their time and face a lot of challenges when dealing with data preparation. For this purpose, it is important to have appropriate tools to facilitate the data scientists in this regard. Typically, such a pipeline has different stages, starting from data discovery to data integration and data readiness. We are trying to facilitate tasks across this pipeline. For example, for data discovery, often there are several data sets, for example, a data catalog, and data scientist is looking for which of these data sets might be appropriate for the task, for the model that has to be trained. Then there are often issues relating to the fact that descriptions of the data sets might not be very complete, or it might be difficult to compare different data sets and find out which one is more suitable and so on. Also, in many cases, there is a need to integrate data from multiple sources. And again, this faces many problems, like the fact that entities in different sources usually do not have global identifiers. Also, when we're dealing with geospatial or temporal data, resolutions might be different, and there are issues about alignment. And again, when we get to the part of training the model, often there is lack of labeled instances, or there might be issues about data bias that are not very easy to detect, or overall lack of enough training data, which calls for tools for synthetic data generation. So these are the kind of problems that we are dealing in the project, and what STELAR is developing and providing is what we call a knowledge lake management system, or KLMS for short, which supports these actions for fair and AI-ready data in this context. The KLMS essentially comprises of two main parts. On the one hand, we have the platform, which is a set of core components that support data publishing and searching for datasets, especially about tracking workflow metadata and dataset metadata and connecting this metadata into a knowledge graph. And on the other hand, we have a set of tools that support activities about describing datasets, interlinking, and annotating datasets. These are some predefined tools that we have developed in the project, but they are indicative, and it is possible for someone to develop additional tools and integrate them in the platform. The platform and the tools are designed in a way to be more general. However, the use cases we have selected and the pilots we are conducting are specifically in the agri-food domain. And this was on purpose because we think that there are lots of data challenges there, maybe lagging a bit behind compared to other sectors. So we have a lot of interesting problems to deal with. A few more words about the platform. So the platform is intended to support the typical data science scenario where a data scientist starts with some data sets and performs a series of actions like cleaning, integration, annotation, and so on, in order to prepare this data and train models. And a common challenge there is that you might have many alternative workflow designs, different configurations. So this leads to multiple executions when designing the workflow, but also when monitoring a workflow in practice. And for this reason, what is important and what the KLMS platform supports is to track metadata both for the input and output data sets in these operations, and also the configurations and the performance metrics of the workflows, in order to be able to monitor what is happening and to compare different executions, get insights, and optimize the workflows. In terms of the tools, we provide several tools. I will not describe everything in detail, but as you can see here, we have tools for data discovery, for example, profiling data in order to enrich their descriptions, or summarizing data in order to better and more efficiently cope with large volumes. We have tools for interlinking, like doing schema matching and entity matching across different sources, or aligning time series and fusing time series, and tools for annotation, like entity extraction or field segmentation. So as you can see, some tools are more generic and some tools are more tailored to the use cases that we have in the project. And speaking about the use cases, I will also say a few words about the pilots. We have 3 pilots in the project. The first one focuses on food safety. So here we're dealing mainly with textual data. And one of the challenges that we are trying to address is how to extract structured information from textual unstructured data, like food safety reports. These are documents that describe a food safety incident, and from this, someone needs to extract what was the hazard, what was the ingredient, the brand that was involved, and such kind of things, in order to support warnings, extract insights, and try to mitigate or even predict risks across the food supply chain. Then in pilot B, which we'll also see later on in more detail, we turn our focus on remote sensing data. And here the challenge is how to make early crop yield predictions. This can happen at different levels of granularity. For example, at the farm level, it is important in order to provide support to the farmer for better decision making. But also at a larger scale, like a whole region or even a country. This again is very important to support food security via early warning. And last but not least, our third pilot focuses on precision agriculture. And again, here we have several use cases which focus around the challenges of integrating multiple different data, for example, meteorological variables, agroclimatic indices, soil indices, and so on, in order to support decision making, for example, to develop high quality suitability maps to support farmers in their decisions. And with this, I conclude the summary of for the STELAR project. Again, thank you very much, and I'm available for any questions if there is something later on.
Thank you, Demetrius, so much. It's great to see such a well-structured project and which has so many relevance across the board, from food safety to precision agriculture. And I believe that this is also a focal point for our upcoming presentation, and that is Victor's presentation on CrackSense. Thank you.
Thank you, Marina, and thank you, Dimitri, for the nice presentation of STELAR. Very interesting, and as Marina said, it has several points that they are similar to what we do, but we are going from the thematic point of view. I will present in 10 minutes what CrackSense is about, which is utilizing and upscaling sensing and digital data technologies for monitoring and predicting fruit cracking. I'm Victor Alkanatis from the Volcani Center in Israel, a research scientist, and I'm co-coordinating this project with Professor Sadka, Avi Sadka, who is in the audience right now. Our project deals with cracking, and cracking can be found in almost every fruit. We don't see it in the market. We don't see it in the supermarkets, but it happens in the field. And sometimes the cracking, as it can be seen here in the slide, is so severe that the fruit does not reach the market at all. So we would like in this project we address this problem in terms of how can we predict or estimate the risk of cracking and be able to apply some means of mitigation. So fruit cracking has many reasons. Some of them are endogenous reasons, like the tree age, the genetic makeup, the hormonal content, the fruit size and shape, which we do not really have much control on that. Some of them are exogenous reasons, like the climate, soil texture, local conditions. And here too, we do not really have much control of it. And on top of it, we have the climate change, where those changes really affect the phenomenon of cracking in a way that we cannot predict in advance. And there are some other parameters that they can affect cracking, fruit cracking, which there are management more parameters like plant growth regulators, mineral nutrition, and irrigation, which may serve as a control signal of the farmers in order to mitigate fruit cracking. Just to describe the type of problem that we are dealing with, this is a mandarin, a seagull mandarin developed in Israel, which is very high quality mandarin, but has a very high problem of cracking. In Israel in 2022, in the north part of Israel, over 60% of the yield was cracked, which makes it unmarketable. And in the center of Israel, about 5%, in the south of Israel, about 10%. So this is a problem that is all over the country. And this problem also, it increased with time. And the area that was cultivated by this very high quality mandarin decreased a long time. So if we have an annual yield loss from 10% in the 2000 up to 50 to 60% in 2022, this makes this mandarin unmarketable and not profitable for farmers. So our purpose or our goal was to use proximal and remote sensing technologies, including 3D temperature point cloud data, and using also edge units that support crack detection, the first crack prediction as a second, and then in the different scales, in the fruit scale, tree scale, and plot scale. By combining all those technologies together, we are trying to link the data that we compile from those technologies to models that they can help us mitigate or try to see how to mitigate the risk of cracking. The cracking, this project has the first, maybe the most straightforward purpose to estimate the cracking intensity, which is by looking at the fruits at different levels and at the trees. Then upscale the sensors technology to estimate the yield loss due to the cracking. And maybe the most difficult task would be the assessment of the risk of cracking before it happens, so that we can say to the farmers what is the risk in their field, and they could use some mitigation techniques when possible. The project tries to address in different scales. In the fruit scale, where we monitor the fruits, both for detecting the intensity of cracking and also predicting the risk. Looking at the tree level, well, the tree analysis gives us some information about how the tree health and tree status can be used in order to estimate and predict the cracking intensity. Then we have the whole plot synthesis of the individual trees, where precision agriculture comes in, define the variability in the cracking phenomena in the field, how it is distributed, and if we can use different techniques of precision agriculture in order to address the cracking in the plot. And then we have the regional integration, where more large-scale parameters can be used in order to estimate the risk of cracking per field or per region. We are 14 partners from several countries in Europe, as you can see here, from the north to the south. We work on 4 different crops: sweet cherries, pomegranates, table grapes, and citrus. In the first 2 years, this is a 4 years project. In the first 2 years, which have already passed, we have done controlled experiments where we have applied in purpose some treatments in the plots in order to induce cracking. And we used the sensing technologies that we develop in order to measure the parameters that are later on be used in a model to estimate and predict cracking. So in those 2 years, we have collected a lot of data in different situations, some of them in farmers' standard conditions, and most of them in experimental plots with different conditions than the farmers use. The second part, which began this year, is to use the same technologies in pilot plots. So the data from the first 2 years are used to build the models that are used to predict and detect the cracking in the fruits. And those subsequent years, we are trying to see whether we can use this data in order to really detect and estimate the cracking in pilot plots. We use this in various levels, as I said, in the fruit, tree, and plot and region scale. And in all of those, we use a lot of technologies that they are relevant to the scale that we are working. Up to now, we have 2 seasons of data in 3 agronomic scales in fruit, tree, and plot data. And we still collect a lot of data in many regions. Just some examples of things that we are doing. This is an example of proximal sensing in pomegranates. So we can see the cracks in visual RGB images and in thermal images. In grapes, we can see the cracked fruit that has a very prominent different temperature than the berries in the same grape. And we can see also differences in the spectral reflectance. This is part of what Professor Zude will talk in later about how we use proximal sensing that combines LiDAR and thermal images in order to define and estimate parameters of the fruit that they are related to cracking. Just a very brief example from Israel in citrus of the results. We want to correlate it between tree physiological status as a proxy to cracking intensity. As I said, we had a very different conditions of growing the fruits than the grower in order to produce a wide range of cracking intensity. And a typical result is the correlation between the daily tree growth, or the predicted and the expected, through the models that we build. And then linking between the tree growth and the predicted parameters from remote sensing, like predicted leaf area from LiDAR. And the final goal is to actually link between the cracking and the remote sensed data, the parameter, which is the leaf area in this case. So this would be the type of models that we are interested in doing in order to predict by sensing tools the cracking intensity and the cracking risk. And I think there is a lot of place to think about this cooperation between STELAR and CrackSense in terms of using the data in this specific agricultural field and the type of framework that you built in STELAR as a general model of processing the data. Thank you.
Thank you, Victor, so much for this brief overview of the project. And now we would like to move on to our first stellar presentation by colleagues from Vista, Solveig Blocher and Silke Migdal. Let me know if you can share your presentation.
Yes, 1 second, please. All right. You should be able to see my presentation.
Yes, perfect.
Maybe just a small correction. Actually, Silke won't be presenting today, so you'll have the next 15 minutes roughly just with me. All right. Thank you for having us today. So before I dive into our pilot and into what we do within our pilot and within STELAR, I'd like to introduce you to Vista, so the company I work for. So my name is Solveig Blocher, and I'm a project scientist at Vista, and I do our internal coordination for STELAR within Vista, and I am the leader of Pilot B. Okay, so Vista's core competencies. Our work is based on satellite data analysis. We combine the satellite data analysis with radiative transfer models and crop growth models for different sort of purposes. Our services range from smart farming related services showing qualitative differences within fields to large-scale indicators of agricultural production that support predicting food security on country or continental scale. All of our products are actually available worldwide currently, and the core of our products are field-related products that enable smart farming, like fertilization and so on, or crop monitoring and risk assessment on, or risk management on larger scales, yield prediction, harvest monitoring, as well as sustainability services and carbon farming. So we do this by essentially analyzing time series of optical data, and we derive plant biophysical parameters from that optical data using radiative transfer models. In case you're unfamiliar with this, different parts of the electromagnetic spectrum can tell us different things about our plants. So we can only see a small part of the electromagnetic spectrum ourselves with our own eyes, but there is so much more information when we turn into the infrared spectrum. For example, information on nitrogen uptake, the leaf area index, which we use as well, and the water content of plants. And those plant biophysical parameters are assimilated into our crop growth model PROMET. PROMET can assimilate not just plant biophysical parameters, mainly the leaf area index. It also uses information from soil information, elevation, and meteorological information to simulate crop growth over a season. And since it is a physical model and it doesn't rely on any sort of statistical data, it can also do those sort of simulations rather well during extreme years like 2018. And what's actually really cool, since we usually do actually a full season of our yield predicting services over Europe, we usually start with Spain in spring and then move further north as the growing season progresses over Europe. And you can see this here really nicely through the BCH or phenology plot or development over Europe over time. Our, is this moving? Okay. So our satellite information is updated pretty regularly. We usually use Sentinel-2 data, where we have a new scene every 2 to 3 days over Central Europe. That also means that with every update of satellite data, we can update our model runs. So with every satellite data update, we actually do update our model, or we run it again. And over time, the picture that we get from feeding satellite-based or satellite-derived data into the model becomes clearer and clearer until we end up with our final yield maps. All right, so how does this fit into STELAR? Our pilot is, as the title, early crop yield prediction. So within our pilot, we address two main challenges. So for one, modern agriculture requires consistent information for decision-making processes. And since plant growth is a highly dynamic process, let me move this. It is a need for up-to-date information. So we need reliable information, reliable data from satellites as frequent as we can to actually monitor crop growth properly. Our primary aim within the pilot is to have reliable yield predictions as early as 8 weeks before harvest for different kind of crop types. Our pilot is separated into 2 use cases, which are very similar in terms of what the end result is, but are distinctly different in how we get there. So our first use case is called yield prediction for agricultural decision making. And in this case, we actually already have a lot of information of what's going on the ground. We have field boundaries that are provided from farmers. We know the crop type, so we understand how the plant develops over time in an ideal space. We understand how biomass allocation works within the plant, and we know when to expect the mass amount of biomass leaf area index maximum, and we know when it's supposed to be harvested. Our second use case is food security through early warning. In this use case, we have a lot less information. We run this kind of use case on, I'm not sure if you're familiar with regional levels in your group. We run this on NUTS2 levels, which is a sub-regional level within a country. And there we don't know the crop types. We don't have field boundaries. We don't have a lot to work with. So in this case, we need to find our field boundaries from satellite data. We need to find our crop types because yield predictions are always done crop type specific. And when we have those, we can do the time series monitoring, time series analysis. The tools that are being demonstrated within our pilot are 4 to 5 in total. So we have the EO data fusion. With the EO data fusion, we try to fuse different satellite data from different sources and thereby leverage multi-sensor information. With the time series imputation, we try to improve the time series continuity by using state-of-the-art deep learning methods. The field segmentation, which gives us the field boundaries where we don't have them, tries to improve our knowledge base through the analysis of spectral information. And lastly, the crop type classification uses LAI time series to actually get the crop type which we need in turn for proper yield prediction. The data that we use is split into 2 parts. So for one, we have the leaf area index from optical satellites such as Sentinel-2, A2B, Landsat 8, and Landsat 9. And we have those as a time series for the entire agricultural season for parts of Austria and parts of France for the year of 2021 to 2023. So Sentinel-2 A and B are European satellites. Sentinel 8 and 9 are NASA satellites, and they detect roughly the same part of the electromagnetic spectrum. So though not quite the same, but enough to make the data comparable. The spectral information that we use comes solely from Sentinel-2 A and B. And the spectral information is mostly used directly in the field segmentation, but also in the radiative transfer modeling where we get our LAI time series. So just can show you what the KLMS looks like. For the KLMS, at least from my side, is mostly a website where I can look at data, where I can look at the tools and define workflows to define different kind of data analysis tasks. And from there, I can choose my satellite imagery, like the imagery that we have for different Sentinel-2 tiles for 2022, 2021, for example, for the tiles 33 TUN or 33 UUP. And from there, I can start the process, wait a couple of hours, and then I have my time series ready for downstream tasks, for example, to feed them into a crop model and do the prediction. Within a pilot, we processed nearly 1 terabyte of satellite imagery from Sentinel-2 A and B Landsat 8 and 9. We demonstrated the tools like the time series imputation at different scales. So we do this for a few 100,000 fields when we go to larger regions, or we can do this on separate fields where we get the field boundaries from farmers and do a little bit more advanced analysis, considering that we don't have the mass amount of data that we need to be aware of. Once we have the LAI time series for our respective fields, either for the large regions or for single fields, we can take a look at how the yield that we have distributes over a given area. So we can see how distinct the yield is. We can compare it to previous years, we can compare it to other regions, and thereby give an estimate of how the yield will develop this season and if there is any need for risk management in a given year. All right, this was all from my side from a pilot B. If you'd like to know more about what we do at Vista, come visit us at our website. If you'd like to know more about STELAR, or maybe actually try the KLMS yourself, you're welcome to do this through sandbox.stellar.ngr. You don't need to go through 1 terabyte of data to actually have your own little time series analysis. We have predefined workflows and walkthroughs already at hand, so you can test the data and demo sets, see how it fits, check the KLMS, the capabilities, and so on. So you're very welcome to join us there and take a look at the outcomes of STELAR. And with this, thank you, and that is it for my side.
Thank you, Solveig, so much for this comprehensive presentation. I would like to give floor now to Manuela Zvuzdasase. Manuela, thank you for joining us today. And after that, we will proceed with the Q&A session.
Yes, thank you so much for giving me the time to explain a little bit what we do. I'm a work package leader responsible for the proximal sensing at the fruit level within CrackSense. My name is Manuela Zvuzdasase. I work in Germany at the Leibniz Institute of Agriculture and Engineering and Bioeconomy. So also I would like to explain a little bit what we did in the past and then how we entered the project and what we have so far. As Victor said, the project is still ongoing, so we are in the middle of everything basically, which might be a good chance actually to interact with the AI model with STELAR and to see what we can maybe do together. So just to have a little bit of the framing where we work. So we have when we think about cracking, we have different data sources at different levels actually. So we can what you see on the left side here, and what we basically do in the work package 2 is we work with close range remote sensing with different sensors. we definitely need to make a choice of the sensor. We needed to do that. And I would like to give some introduction for the reasoning why we use the sensors that we finally used. For the moment, this close-range remote sensing is used a lot in irrigation models so far, also a little bit in heat stress risk models, while application and fruit cracking models is rare or not existing actually. So here we are pretty new considering the methodology, but I think also in other applications it might be interesting to insert this kind of technology more because yeah, we do get data at the fruit level. So if we just for picturing it again, what we just heard, so if we work on with satellite data, we see the field like this, and then if we work with a UAV, we get a little bit closer. We can even go at the tree level. And then if we do close range remote sensing, we can go for what we see in false color here, in blue, the whole canopy, and then marked in red, apples here. So this is where we want to go. But then the question is always also, what is the choice of the sensor? So there are several ones. I listed a few in the slide before. So the challenge that we are facing is we have this green canopy and we need to find the fruit somehow. So but then we have specular reflectances on the leaves and on the fruit. We have green leaves and green fruit, so also radiometric information might not be the best to select fruit. And then we have occlusion, so we still see fruit here, and basically what we see with the sensor is most often the surface only, and then in the back it's basically black. So what we need to do is we looked in the literature first and actually wrote a review before the project already, and then saying what is done for detecting fruit size, for example, because then if we can detect the size quantitatively, we are sure to work at the fruit level in a reasonable way. And we looked a lot of AI models are used actually for fruit size detection. Most of the papers out used RGB, a few used RGBD, where we also get the depth information. Hyperspectral is also pretty common. Some of the colleagues fused with thermal imaging. And then we found that in recent years, LiDAR is getting more prominent, are not giving exactly better R squares, but well, LiDAR has the advantage that it is pretty independent from lighting conditions. So the shading occlusions inside the canopy would be less of a problem then. So we said, so we would like to go for the LiDAR. And this is what we did then. So we at ATB, Leibniz Institute of Agriculture, Engineering and Bioeconomy, we built this railway system, something like a roller coaster. So we transport sensors around the fruit. The whole thing is 100-meter long, so we can monitor the trees automatically, basically 24/7. And what we do is we pass the sensors along the tree row. And what we get then is first with a laser scanner, we get the geometric information of the trees. It's nice because you get point clouds, so you can turn, you can look inside the canopies, but you also can have a look on the fruit. And I would like to mention also that we have the geometry from the laser scanner, but then if we work also with a return signal strength intensity, we get some intensity value. So we try to use a laser scanner that is emitting at 660 nanometer, which is a wavelength range where the chlorophyll is absorbing. We did a very fast experiment, so we selected banana because they ripen so quickly. So we placed a banana in front of the laser scanner, so this time in the laboratory, not outside. We passed it along the fruit, and then we see here in false color the different intensity values that we got. We see marked here where we got the chemical reference analysis, and we see something like a correlation. Can all be improved with multivariate method, with AI, but there is a relationship at least. So that means we are able to see, to work on the radiometric data. And then we thought it might be good also to add the fruit temperature, because in CrackSense then later, and actually we had this approach, and then we said, well, it could become potentially interesting in CrackSense as well. We have a laser scanner and a thermal camera, and then we fuse the data. This is what we did on this conveyor roller coaster, where we have stable conditions. And we fused to get the temperature distribution finally in 3D. But as said, with these stable conditions, it's a fixed setup and everything. So we said, if we want to go for cracking, the temperature is an issue. So this is what the colleagues, mainly from ARO, but also from INRAE and from Germany, from VGA. So what they told us, they need the temperature, but also the wetness on the fruit and the duration of the wetness on the fruit. So that means we needed to find a system that can measure the fruit temperature distribution in the field and also predict the wetness. And we wanted to do it with different partners, as Victor explained. So we are doing the exact experimental trials, but then we also have a lot of pilots where we collect data, and it should be definitely mobile. So what potentially we could get is we could get these canopies marking the apples, and then what we see here on the left, so the fruit are marked here in orange, and we can get the temperature of this fruit. So we can have here on the right side, we see a diurnal curve, and in yellow triangles, we see the daily temperature fluctuation, day and night. And we see how the fruit temperature is following these curves, but only following because of mass. There are thermodynamic models out, so this is easy to explain. But we cannot assume that the air temperature equals the fruit temperature, so we really need to measure. Plus, we see in these box plots that there is quite a distribution here. So some fruit have higher or lower temperatures than others. And this is exactly what we wanted to see, and potentially on thousands of fruits, which is interesting for AI also. So what we started is we started from the scratch and built up a completely new system. So with all electronics, software, completely new. It has to be energy autark so that we can use it in different fields, including the pilots, where there's basically no power supply, nothing. So it has a router, an edge unit is connected. So if there's more questions on the edge unit, Serjan from Wislor, company Wislor, is attending this meeting. So we started with a prototype, and then finally we ended up with this system that we call TOMI, Terrestrial Orchard Monitoring and Measuring System. And we mounted 3 sensors. So one is a laser scanner, a thermal camera, and an RGB. So now we have this autark system ready, actually 4 units of those. The systems, these 4 units, were distributed to the project partners so that we can do measurements with exactly the same methodology, with exactly the same systems, the same settings, which is super nice for AI applications. Because there is no more metadata needed, no more labeling, that maybe integration time was changed here and something else was changed in the other side. We have all standardized measurements in all plots. That is a nice thing. So we have the sensors, but now we needed to fuse the data. This is what we do with a calibration step. So we have an active target with lamps. We present it basically to the sensors in different ways. So then there are algorithms to fuse the data. And what we get them is this kind of temperature annotated point clouds with the TOMI systems. The algorithm is open access, so it can be reproduced. And we see here in false color already are the different temperatures within the canopies. We can assume that there are some fruit here and there already. So that works nicely. What we see here in blue is artifacts. This is always when the laser scanner and the thermal camera hit the sky. So we get the bed temperature, but here in this range, we are sure that we hit a surface of the canopy itself, so we can work on those data. As said, we have those systems out now. The fourth system is missing. Actually, it's ours. So we have one at INRAI measuring on sweet cherry, and a little bit on citrus. We have one in grape and citrus and pomegranate, grape, pomegranate, citrus. This is basically what was mentioned also by Victor. So we have the systems there, and we go to the pilots right now. Experiments were so more concrete experiments were done already. So we have those database, which is stored in Greece, actually. Also, we have open access data. This database is fed throughout the last period of the project now. So we collect the data from all the partners, including the pilot, and then we bring it into an open access database so that data scientists, for example, can use it afterwards, or plant physiologists being interested in fruit temperature, fruit size, and fruit wetness, or they can access it later and do also physiological modeling maybe. So just to delve a little bit more on what we get here. So we get the fruit size as said. So we use Fourier analysis to calculate the shape, also for dimension reduction, to calculate the shape. So again, here we see an example of the apples. We measured a lot in parallel also on apples because we have it in front of our door, while the other data are still in processing mainly. So this is a very small apple, still young apple, 60 days after full bloom until harvest, 151 days after full bloom. And we see on the right that how the shape is changing. That is the Fourier signature that we use then to calculate the size from the different fruits that we found in the field. So these are fruits that were found at the trees, point clouds of those fruits that were found at the trees. We see that in the lab and in the field, there are differences. So let's say in the field, because that is the worst result, we get something like a root mean square error of 4 millimeter, which is super good if you compare that to what can be found in the literature. So we have the size with the Tommy. We do have the annotated temperature. We see here the live image, how the laser scanner finds the cherry fruit, and then how the thermal camera sees this cherry fruit. So we have not even one value per fruit, but a distribution again on the fruit surface that we cannot reference because we can only take one reference with a handheld thermometer. So, but comparing this one manual reference with a mean of what we see with a Tommy, we come up to an error of 1.7 Kelvin, which is quite an error, but it's maybe not so bad for example, cracking prediction. If we only, so actually the error is 1.75 because we cannot, from the beginning, we cannot exclude that we have wet surfaces. So if the surface is dry, we have an error of 1.7. If the surface is wet, we are basically measuring also the temperature of the water film on the surface. So that's why if we exclude fruit which have a temperature below the dew point, then the error is a little bit decreased. And that's the point actually. So having the dew point available, the dew point of the air, we can make an easy prediction from the fruit temperature if there will be condensation on the fruit or not. So, and that is the third variable that we get from the Tommy. So we wanted to predict also the wetness. So we did reference analysis. So we had a protocol to classify visually fruit at different wetness stages. So completely dry, a small micro drop, the drop increasing a little bit, and a whole water film on the whole fruit. And we tried to predict that just by saying when the fruit temperature is at the dew point, there should be a change. This is what we did already. So the next step is then also to use more AI and compare it with a thermodynamic model. Not sure what will be better, we will see. Yep, so this is the state of what we have so far. So we have the system, it's out with the partners doing measurements, and we get these 3 variables which are important for cracking at the fruit level. Thank you so much for attention. Oops.
Thank you, Manuela, so much. So we are just in time. I just wanted to ask the participants if they're willing to extend this for a couple of more minutes in case there are questions from the audience. So is there anything that somebody would like to ask that applies both to the presenters? If you find something interesting to discuss at this point, I have written down several interesting topics that we can discuss. So Victor asked, what crops are included in the yield forecast?
Yeah, so we do the yield forecast within STELAR for winter wheat, grain maize, sunflower, winter barley, and soybean.
Thank you. This is something that I also wanted to ask both you, Solvig, and Manuela. I wanted to ask how type of crop affects data collection and data outputs. Are there any differences depending on the crop? Because both of you have highlighted that crops are main reason why these recordings may differ.
Yeah, maybe from the Tommy side. So the fruit size does matter. So if we have very small fruit, they might be a little bit more difficult to find in the canopy. Actually, it is a little bit easier doing it manually than doing it automatically. So there is still some room for improvement. But that is one. Others is no. So the rest is fine for all the fruit crop.
Thank you, Manuela. Solvik, would you like to respond from yield prediction angle?
Yeah, so the difference in crops is to one part the situation that our crops grow in different parts of the year. So winter grains are usually planted in the fall before the year they are harvested in, which means we start collecting data in spring and then move through the summer until harvest, which is usually in Central Europe sometime in early August. Although this year we're actually quite early, we're nearly done here. And our summer crops like grain maize, they start a lot later. So we start monitoring around May, June-ish, and then move all the way through October. And that also means that during data collection, we have different limitations in terms of cloud cover, because optical data, you can't really see it through clouds, but you still need that sort of information. And when we're in Central Europe, data quality is usually a lot better in June, July, August, but that might not be enough time to get the full picture of plant growth. And a second part is why we differentiate between the crop types is because they have different responses to, for example, drought. And for every plant, it goes that during the drought response or the stressor response always depends on the phenology. So very small plants, usually a bit more easily stressed by drought or not enough water than plants that are a little bit larger and have deeper root systems or are already later in plant growth where they just with drought stress just doesn't matter that much anymore.
Thank you so much.
May I add just one more small thing? If you can comment about how do you validate the yield prediction, the yield forecast? If you measure with yield monitors or a mean yield per field or whatever else.
Well, within the field-based pilot, we have validation data from the farmers that we collaborate with. So since we're doing a hindcast in theory, we set up the system as we would in a regular season. So we use different time steps for the simulation, but we always compare against the data that we already received from them. For the larger scale use case, we validate against statistical information. So usually from Eurostat or something similar.
Thank you so much, Victor. I believe that this is the question that you have also posed in the chat. So I can proceed with a question from Dalibor. For Tommy application, he also said great presentations, by the way. For Tommy application, how steady shall be the platform while recording the images with sensors?
Actually, the platform is like you place it in front of something like 1 or 3 trees, depending on the size of the tree. And then we have a 2D laser scanner. So the whole system moves this group of sensors from one side to the other side of the Tommy. So, and by moving it, we make from the 2D, we get then the 3D information. And maybe also just for the next question in my direction, because I need to leave in a minute. So how do we get the label data about the cracked fruit? So we discussed with the whole group, and then we found about this cracking index. That means we have for the temperature, it's like we take reference measurement on the fruit. For the wetness, we have these 4 classes of wetness. And for the cracking incidence, I would like to hand over to Avi actually, because he knows better about this cracking. But what we do is always when we run the Tommy, we have a subsample where we also take those references to be able later to do test set validation.
Thank you, Manuela. Avi, would you like to elaborate?
Oh, thank you. No, I'll.
Thank you so much.
Yeah, actually, basically, we recorded the number of cracks appearing, and then we noted it.
Thank you, Manuela. We also have one more question by our coordinator, Avi, to Solvik. How accurate LAI determination from satellite as compared to UAV-based methods?
Actually, I'm not familiar with UAV-based methods. Zilke, maybe you have some experience with that?
Yeah, let me take that question. Because in STELAR itself, of course, we have no UAV, so there's no comparison there. But we did these comparisons in earlier projects and earlier years, both with UAV-based methods as well as also with LAI sensors on the ground. Of course, the UAV methods have a higher spatial resolution. So if you want to see individual trees and individual fruit, you have a higher spatial resolution if you are flying lower than the satellites. But often in UAV-based methods, what you do not have in as much accuracy is how the plane was flying. And that is very, very necessary because depending on the way you look, if you look away from the sun, if you look into the sun, if you then have the geometry of the crop as well, that gives you different results in your spectra and then different results also in the leaf area. And that is something that satellites are very good at knowing. So you have very straightforward angles, which makes it much easier to get also a very stable leaf area value than from UAV methods. So in that way, satellites have an advantage, even if they have the spatial disadvantage of being 10 meters right now for free data anyway. All right.
Thank you. Thank you so much. If there are no more questions from the audience or from the presenters, I would like to once again thank you all for this amazing presentation and for sharing such a vital part of our research and our contributions to precision agriculture, food safety and security. I believe that both projects have so many things to contribute to when it comes to global and Europe food production. I hope that this webinar will stand also as a inspiring point for future collaborations, for future knowledge sharing, and we cannot wait to see what more will these projects bring to the table. Thank you once again, and hopefully see you soon in similar occasions.
Thank you very much.
Thank you
very
for
much.
organizing.
Thank you.
Thank you very much.
Have a nice day.
Thank you. Bye.
Have a nice day.
Goodbye all.